Okay. So today's webinar will provide an introduction to FAST, which is the U.S. Geological Survey's public domain reactive transport model. FAST uses FreakC as its geochemical modeling engine, but also provides full 1D, 2D, and 3D flow and multi-species solute transport modeling capabilities. We will briefly go over what reactive transport modeling is all about, provide an overview of FAST, and then go through a relatively simple 1D example to show how to set up a FAST simulation. We'll then show an extension of this example into 2 dimensions, take a break to answer questions, and then move on to a second 2D example problem. Okay, so in a nutshell, reactive transport modeling involves dividing up a portion of the subsurface into a series of boxes, solving the flow and transport equations to quantify mass fluxes between the boxes, and then modeling all of the relevant geochemical reactions within each box. All of this takes place over a small time step. Species concentrations are updated, and the process is repeated for the next time step. So consider some of the details. The reactive transport model, first of all, must solve for the water fluxes driven by a hydraulic head gradient, as well as external sources and sinks of water. This is in much the same way as a groundwater flow model, such as ModFlow, must work. Second, the model must also handle multi-species advective dispersive solute transport with external sources and sinks that are linked with to any of the external water sources and sinks. And then finally, geochemical modeling basically occurs. This handles internal sources and sinks that stem from mineral precipitation dissolution reactions, surface complexation reactions, and cation exchange, for example. In the case of FAST, this involves using FreakC to redistribute solute masses within each cell or box within the model during a particular time step. I should note that this step is quite computationally burdensome and contributes to the long runtimes that are typically associated with reactive transport modeling. I should also mention that there are different approaches that exist for coupling the groundwater flow transport and geochemistry equation sets together. The so-called one-step approach solves all of the equations together for each time step, which is conceptually robust, but is rather complex to implement, as you might imagine. In contrast, the two-step or operator splitting approach, as it's sometimes called, separates the flow and transport geochemical modeling steps over small time steps. FAST uses this operator splitting approach without any iteration between the transport and geochemistry portions of the model. Those of you who are mathematically inclined, this is just a summary of the equations the reactive transport model must solve, at least in some form. The first is the conservation equation for groundwater flow, which can be either transient, as shown here, or steady state. The second equation computes groundwater velocities for the advective component of solute transport from Darcy's law and the effective porosity. The third equation is a complete expression for the advective dispersive solute transport equation, which includes source sink terms that involve mass transfer between gas or mineral phases and water, as well as surface reactions. Directly solving this third equation is what the one-step approach is all about, whereas the operator splitting approach breaks this into pieces. The take-home message here is that there is a lot of computational complexity involved in either case. Okay, now let's talk about FAST itself. As I mentioned, this is a public domain model from the U.S. Geological Survey, which uses FreakC for its geochemical modeling engine. The flow and transport modeling functionality is provided by HST3D, which is a 3D finite difference model. The code can be freely downloaded from the link provided here, be sure to download the batch version of the model, which works off of text-based input files and keyword blocks. We'll be using this for the course. I should mention that the user's manual supplied with the FAST download is an excellent resource in terms of learning how to set up the model, apply various boundary conditions, and so forth. There are a few limitations to FAST for you to keep in mind. As I've mentioned, it can be very slow. Complex problems with many species and reactions, especially if kinetic reactions are included, that are distributed across a finely discretized 3D model domain, can potentially take days to run. As far as physical processes go, FAST does not model the flow of multiple partially miscible liquids, nor does it directly model the unsaturated flow of water through the Vadose zone in accordance with the Richards equation. Finally, and this is a key issue for some problems, FAST does not update the porosity or permeability of the aquifer material in response to mineral precipitation dissolution reactions, which could, in some instances, directly impact pore volume. However, for both of these last limitations, there are some approaches for circumventing them, using outside calculations and updating the FAST model as the simulation runs. I'll return to this particular topic in the next 2 webinars, but won't discuss it today in any detail. So despite all of the complexity, it's, I think, remarkably easy to set up a FAST simulation. Only 2 input files are required, although additional files can be used to describe heterogeneities, initial conditions, and so on. So first, the chemistry input file looks just like a Freak-C input file and lists the solution chemistry, phases, surfaces, kinetic reactions, and other keyword blocks that describe the geochemistry considered across the entire model domain. The contents of each keyword block end up being assigned to different portions of the model grid as initial conditions using index numbers, as we'll explore in an example here in just a bit. The transport input file is also keyword block oriented. Within this file, the flow model is specified as being either transient or steady state. The top layer is designated as confined or unconfined. The model grid is delineated, physical properties of the porous medium are defined, and a host of various boundary and initial conditions are specified. Again, index numbers are used to link different features in the chemistry input file to the transport input file. As far as physical properties, boundary conditions, and initial conditions go, there are a variety of tools to use to fine-tune assignments to blocks of grid cells, including reading arrays from external files or using GIS shapefiles, and geometries such as prisms or wedges. FAST creates 3 principal output files that can be used to directly plot the model results. These include a chemistry output file. This lists the dissolved concentrations, mineral masses, etc., as a function of location and time. And this is as a tab delimited table with listed constituents provided in a selected output block in the chemistry input file. Separately, groundwater head and groundwater velocity distributions are also written to a comma delimited text file, and these are organized again by location within the model domain as well as time. With all of that being said, let's look into a specific example, in this case, an ore forming process, and see how to convert it into a simple, relatively simple FAST model as a demonstration. Supergene copper ore deposits are formed in response to groundwater flow under changing oxidation reduction or redox conditions. The primary ore consists of chalcopyrite, which exists together with pyrite. Both minerals are stable under reducing conditions. However, following, let's say, tectonic uplift or a drop in the groundwater table for some reason, part of the ore body becomes exposed to atmospheric oxygen. This causes dissolution of the primary ore sulfides, perhaps enhanced by the pH drop that's associated with the generation of sulfuric acid as the sulfides are oxidized. Other secondary copper-bearing phases can precipitate in the unsaturated zone that may be more stable, such as malachite or cuprite. At the same time, elevated concentrations of dissolved copper are flushed downward to the water table. There, reducing conditions are encountered once again, and new secondary ore minerals such as bornite or covellite may form. This can represent an enrichment zone, if you will, of the ore deposit. So our goal here is to set up a simple, fast model of this process. Here's a cartoon-like conceptual model of such a system with only the essential defining features depicted. The model domain consists of a vertical one-dimensional column, which is divided into an unsaturated zone in the top portion and a saturated zone toward the bottom. A steady state flux of water passes through the column. A series of possible mineral phases associated with the primary ore material or its potential weathering products are also listed. Other mineral phases that are part of the model in this particular example are potassium feldspar, kaolinite, and dolomite. And the latter is included as a trace carbonate phase present, let's say, in some of the fractures that may be present in the system. So a key principle with which to operate a model system such as this is not to hardwire in any particular reaction in a particular part of the model domain. Instead, the goal is to have FAST simulate the system and precipitate or dissolve certain mineral phases in portions of the model where each respective reaction is calculated by FAST to be favorable. Things work out, FAST results will match up with reality, at least to some degree. So in keeping with this philosophy, bear in mind a couple of things. One is that any mineral phase present initially in the model will have a finite mass that is specified. So potential mineral phases that will be included as equilibrium phases will not have initial masses specified. The initial mass will be set equal to 0. More on that in a moment. Only equilibrium with atmospheric oxygen differentiates the geochemical environment between the unsaturated zone and the saturated zone. And that's the second thing to keep in mind here. I want to stress that this is a very simplified conceptual model we're putting together for demonstration purposes. We can certainly add much more complexity to this in terms of the phases that we're considering, putting in reaction kinetics, expanding the model to 2 dimensions and considering flow heterogeneities and so on. So just something to bear in mind here as we move along. Here's what the chemistry input file looks like for this problem. Solution 1 represents the influent composition of the column. It has been equilibrated with atmospheric oxygen. That's where the log saturation index of negative 0.7 comes in. That corresponds to a partial pressure of 20%. And there is a fixed CO2 partial pressure. And the solution has also been equilibrated with potassium feldspar, kaolinite, and dolomite. Think of this as, if you will, as a solution that's been sort of equilibrated with shallow soils in the area, and it's entering the column through the ore zone via some sort of a fracture or fracture zone. Solution 2 represents pore water that is in equilibrium with the primary ore body. So note the low PE. This indicates reducing conditions generated when pyrite and chalcopyrite partially oxidize and remove essentially any dissolved oxygen from solution. The equilibrium phases blocks represent both zones. Note that the only difference between the two is the presence of atmospheric oxygen in the unsaturated zone. The listing and the starting quantities of the other phases are otherwise the same. In both zones, only pyrite, chalcopyrite, potassium feldspar, kaolinite, and dolomite are initially present. This is what the transport input file looks like. Like the chemistry input file we just reviewed, this file should be included in the class materials for you to download. But I will also include a copy with the webinar slides when I send them out later on today. So you can inspect this at your convenience. I'll point out a few of the keyword blocks starting from the top left. The grid is defined only in the vertical direction for this example, or along the z-axis. The resultant column is 20 meters in length and is divided into 50 cells. Note that a cell is defined by corner node points. Hence, there are 2 node points in the x and y directions. These are basically representing one cell in each direction, and correspondingly 51 node points in the Z direction for all 50 cells. Under the media keyword block,